Welcome to The Explainer. Today, we're going to talk about some of the cleverest tricks your computer uses to do a lot with a little. We're diving into a special class of algorithms that are absolutely key for efficient coding, especially when every single byte of memory is precious.
I mean, have you ever stopped to wonder how your phone can sort thousands of photos without just slowing to a crawl? You'd think it would need a huge amount of extra space to shuffle all that data around. Well, the secret isn't magic. It's actually a really powerful technique in computer science for being incredibly smart about how memory is managed. And that technique is all about a class of methods called in-place algorithms. The big idea is actually pretty simple. Instead of making a whole new copy of your data to work with, you just modify it directly right where it is. So today, we're going to break down exactly what these algorithms are, why they are so critical for performance, and maybe most importantly for some of you, how understanding this can give you a huge edge in your next technical interview.
Okay, so to really get why this is such a big deal, we first have to understand the problem they're designed to solve. And that problem is all about what I like to call the memory squeeze. You see, in so many real-world scenarios, using extra memory is either flat out impossible or just way too expensive. Think about the tiny chip in your smartwatch or an embedded system in a car. They just don't have memory to spare. Or on the other end of the spectrum, imagine a massive server trying to process a data set that's gigabytes in size. You just can't afford to double your memory usage. And that's exactly where in-place algorithms shine. They work directly on the original data, which also makes them really fast because of how computer caches work. It's no wonder they're a staple of coding interviews. They really test how you think about space and time. Okay, so we've established they save space, but what does the term in place really mean? From a technical point of view. Let's get a bit more precise.
To get it, you first have to understand a concept called auxiliary space. The best way to think about it is like an algorithm's personal scratch pad. It's any extra, temporary memory it uses that's not the space taken up by the input data itself. So an algorithm that just copies an entire array to sort it, well, that would have a really, really big scratch pad.
Now, an algorithm is officially considered in place if its auxiliary space is O of 1. That's big O of 1, which just means it uses a constant amount of extra space. Here's what that means in plain English. The size of its scratch pad doesn't grow, no matter how big the input gets. So whether you're sorting 10 items or 10 million, it uses the exact same tiny, fixed amount of extra memory. That's the promise. And this right here busts a really common myth. In place does not mean zero extra memory. That's not the goal. You are absolutely allowed to have a few temporary variables, like a single variable to help you swap two numbers. The key, the only thing that matters, is that the amount of extra memory you use stays small and constant, no matter how huge your dataset gets.
Now, there is one little exception to that strict O of 1 rule. For some algorithms that are recursive, meaning they solve a problem by breaking it down into smaller and smaller versions of itself, like the famous quicksort, we also have to consider the memory used by the call stack to keep track of all those smaller problems. And the rule here is, as long as that extra memory grows very, very slowly, logarithmically, or O of log n, it's still considered in place. It's a special case, but an important one.
All right, enough with the theory. Theory is great, but let's actually see how this stuff works in practice. We're going to look at a couple of classic techniques and use some simple analogies to make sure they really stick. Okay, check this out. Picture an array as a row of boxes. Place one finger on the first box and one on the last. Swap their contents. Then move your fingers inward. This is just a brilliant analogy for a super common in-place pattern called the two-pointer technique. To reverse an array, you don't need to create a whole new one. You just start at both ends and work your way toward the middle, swapping as you go. It's so elegant and crazy efficient.
So here's how it works, step by step. You start with 2 pointers, one at the very beginning, the left, and one at the very end, the right. You swap the elements at those two positions. Then you just move the left pointer one step forward and the right pointer one step backward. And you just keep doing that, swap, move, until your pointers either meet in the middle or cross over. And think about it. The only extra memory this whole process needs is a single temporary variable to hold a value during the swap. That's it. That's O of 1 space in action. The memory footprint is tiny and it's fixed, whether your array has 5 elements or 5 million.
Okay, how about a 2D problem? Let's say you need to rotate a matrix, like an image, by 90 degrees. Again, instead of creating a whole new grid of pixels, which would be really memory intensive,
We can do it in place with a clever two-step trick. And this analogy nails it. Visualize a square chessboard. First, fold it across the diagonal. Then, reverse the order of pieces in each row.
So what does that folding and reversing actually mean in code? Well, first, you transpose the matrix. That's the fold across the diagonal, where you swap element ij with ji. Then, for the second step, you just go through each row of that newly transposed matrix and reverse it using the exact same two-pointer technique we just learned. And the results? A perfectly rotated matrix, all done within its original memory footprint. It's pretty amazing. Of course, as is often the case in computer science, there's rarely a free lunch. Choosing an in-place algorithm often means you're making a trade-off. And this becomes really clear when we start talking about sorting. Just take a look at this comparison. Algorithms like quicksort and heapsort are the champs of space efficiency. I mean, O of log n, or O of 1 auxiliary space, is fantastic. But they sacrifice something called stability. So what's that? A stable sort preserves the original relative order of equal elements. Let's say you have a list of people, and you sort them by city. A stable sort will make sure that all the people from, say, New York are still in their original order relative to each other. Quicksort and heapsort don't guarantee that. On the other hand, you have merge sort. It's stable, which is great, but look at that auxiliary space, O of n. That means it needs a whole extra copy of the array to do its job. So that's the choice you often have to make: save space or preserve the original order.
All right, let's bring this all home. How can you use everything we've talked about to really stand out when you're in the hot seat during a coding interview?
So when an interviewer asks you to solve a problem in place, they're not just testing if you can write the code. They're testing your entire thought process. So don't just dive in. The pros will start by asking clarifying questions. Is it okay if I modify the input array directly? Does the recursion stack count towards my space complexity? Then they'll state the trade-offs out loud, like, well, we could use quicksort here to save space, but we'd lose stability. They'll talk about edge cases like empty arrays, and they'll know about common variations of these problems. Showing you can have that high-level conversation demonstrates a much, much deeper level of understanding. And to wrap things up, I've got a challenge for you: the famous Dutch national flag problem. The task is to take an array that only has zeros, ones, and twos and sort it, in place, of course. It's the perfect way to test the pointer techniques we've covered today. Seriously, give it a shot. It's a fantastic way to make sure these concepts really sink in and get you ready for that next interview.